In our previous lesson, we introduced the idea of limits and how they can be similar or different from y values depending on whether the function that they are being evaluated on has breaks in it or not. For 2.5, we're going to practice the concept of limits a little more and also explore the concept of continuous and discontinuous functions. To make this a little more clear, a continuous function is any function that doesn't possess any sort of discontinuity. A discontinuity is what you would probably describe as some sort of break in a function. There are three specific types of discontinuities that feature on functions. The most common type of discontinuity that you'll encounter with functions is the infinite discontinuity, which are sort of like invisible lines that are created on a graph, and the graph can't touch these lines or cross them, even if it continues on the other side of this dividing line. There's a lot of situations that can actually create these within functions, such as having a variable in your denominator because dividing by 0 can create asymptotes, putting negative numbers into logarithms, and even using infinitely negative exponents on an exponential function. This discontinuity is common enough that it has its own name, and it's often referred to as an asymptote. A removable discontinuity would probably be the most plainly described as a hole in the graph, where every single part of the graph exists, but in one spot where there should be a defined x and y value coordinate, we simply have something missing. A jump discontinuity is a little bit different from a removable discontinuity in the sense that a jump discontinuity can still have a hole, but is defined somewhere else along that same x value so as to technically make it so every single x value of the function is actually defined. The graphs that we saw in our previous lesson that had two different left and right side limits were also examples of jump discontinuity, because they were technically defined at every x value since one side had an open circle and the other side had a closed circle. Jump discontinuities are very uncommon, and you pretty much can only create them when you are looking at a piecewise graph. It might be surprising to find, though, that removable discontinuities can also be created within normal functions without needing piecewise things to make it happen. Our assignment today is going to have some more practice of the same fill in the boxes for y values, left and right side, and true limits for a piecewise graph so that we can see some examples of these different discontinuities. But we're also going to have some problems where we look more into the idea of the removable discontinuity and how this could possibly be created. So down here we have a couple of rational functions. On the left, we have x squared plus 13x plus 30 divided by x plus 10, and on the right, we have 2x squared minus 3x minus 27 divided by x plus 3. Both of these are quadratic divided by a linear. Despite this fact, both of these will graph out a linear function, and each of these linear functions will have a hole in it. Our job is to define the hole in these graphs using limits, as they can give us values for things that technically aren't there and we shouldn't be able to get. For each of these problems, we are going to take the rational function, factor the numerator, use one of the factors to cancel out the denominator, leaving behind our other factor, which will be a linear equation. When we graph that linear equation, there should be a hole at the particular x value given by the limit of the function listed below the graph, meaning that regardless of what we find for the limits, f of negative 10 is undefined for the function on the left, and f of negative 3 is undefined for the function on the right, since substituting those values into the equations respectively would cause you to divide by 0. However, we can define the answer to the linear equation by using the limit as x approaches these values. The trickiest part of this assignment may be the first step, so just in case you forgot, let's go over factoring quadratics really quickly. We'll probably do this a little bit more detail in maybe the next unit, but for now, let's just review this so that we can get past it. Quadratic equations that are in standard form, which we have over here, this ax squared plus bx plus c model, if they have rational factors, they can be factored down into two different linear equations, a times x plus p and x plus q divided by a. The a in this factored form is from the beginning of the equation right here, so all you need to do to get this factored form is figure out what p and q are. P and q are defined as adding up to the b value in the standard form and multiplying together to give you the same product that you would get if you multiplied your a and c values in the standard form. It does not matter which of the two numbers you find you assign as p or q, but it's a good idea to make q a number that is divisible by a just to make this formula work a lot easier. For our first quadratic, we have x squared plus 13x plus 30, meaning that our a value is 1, our b value is 13, and our c value is 30. So we need to think up two numbers that when we add them together, we get 13, the value from the middle, and when we multiply them together, we get 30 times 1, which is just 30. Once we figure out what those are, we can put them into our factored form, which will be 1x plus p times x plus q over 1. Since a is 1 in this equation, we could basically simplify this factored form down to just x plus p times x plus q. And this will be true every time your a value is 1. This is probably the more simplified factored form that you may remember doing from previous classes. In any case, there's only a few numbers that multiply together to make 30, such as 15 and 2 and 10 and 3. Luckily for us, 10 and 3 will add together to make 13, so it's fair to say that p and q are probably 10 and 3. And again, since our a value is 1, it doesn't really matter which one of these we think of as p and which one we think of as q. We simply need to put them into the factored form here to be finished with this factorization. For our next equation, we have an a value of 2, a b value of -3, and a c value of -27, meaning that our factored form will be 2x plus p times x plus q divided by 2. So when we figure out p and q, we should probably pick q as an even number. We're going to need p and q to add up to -3, and we'll need them to multiply together to our a times c, which is 2 times -27 for -54. Again, it's a good idea to focus on the multiplication part of this since there's always going to be limited answers. Other than the obvious 2 times 27, there's things like 18 times 3 and 9 times 6. I believe if you use a +6 and a -9, you can have these add together to give you -3, and those will also multiply together to give you -54. So it would be good to say that p is -9 and q is 6, again, since we want this to be divisible by 2. So putting these into the factored form, we get 2x plus -9 times x plus 6 over 2. We can simplify the plus -9 to just 2x minus 9, and we can simplify the 6 over 2 to 3, giving us our factored form of 2x minus 9 times x plus 3. So the two factored forms that we have here are the new numerators for our rational expressions above. Since the left equation had a denominator of x plus 10, we'll be able to cancel that out. And since the right equation had a denominator of x plus 3, we'll be able to cancel that part out. So once we cancel out our common terms, we'll be left with a linear equation of just f of x equals x plus 3 on the left, and f of x equals 2x minus 9 on the right. So here are our two linear graphs, and notice that I've got some kind of rather large points here with open circles to emphasize the spot where there should be a hole in the graph because we cannot get x values of -10 or -3 for these two things respectively. But even with that point gone, we can see what it should be based on the y value of these. If we were to plug -10 into x plus 3, we would end up getting -7. Over here, if we plug in -3, we're going to get -6 minus 9, which is -15, and that is the exact spot that this lands on right here. So we can finish these two problems by saying that the limit as x approaches -10 for the function on the left is -7, and the limit as x approaches -3 for the function on the right is -15. We don't even need to worry about whether or not the left and right side limits agree because linear functions for the most part are continuous, meaning that if you did have a hole anywhere in the graph and you wanted to take a limit, you should always get the same answer as the line approaches from both sides. This might be a little tricky, so don't worry if it takes a little bit of time to figure out. We're going to have a lot of days to work on this technically, so take it easy, and we're going to continue our work with limits next week. That's all. See you soon.